Hi everyone, welcome back to Coding Fab. Today we're diving into one of the most essential libraries in Python, NumPy. Whether you're working with data, building machine learning models, or just starting out with arrays, NumPy is a must-have tool. In this lesson, we'll walk through what NumPy is, how to create arrays, explore array basics, understand indexing and slicing, perform array operations, and even get into broadcasting and linear algebra. All right, let's get started. 1. What is NumPy? NumPy stands for Numerical Python. It's a powerful Python library for mathematical and scientific computing, especially when working with numbers and data in large arrays or matrices. For example, in Python it looks like this. Imagine you're doing math with lists in Python. You try to add two lists. You wanted element by element addition, like 1 plus 4, 2 plus 5, 3 plus 6. And here's the expected result. But Python just combined the lists like this. That's where NumPy comes to the rescue. To summarize briefly, it makes math with arrays super easy and super fast. You can perform matrix calculations, statistics, and even linear algebra. And it's used everywhere: data science, machine learning, simulations, finance, engineering, and more. 2. Creating arrays. There are many ways to create arrays depending on what you need. Here's a list of the most useful ones. First, NP array. This is used to create a NumPy array from a regular Python list. Once your data is in a NumPy array, you unlock all the power of NumPy, such as fast calculations, easy reshaping, slicing, and more. Before anything, make sure NumPy is installed on your computer. In your terminal or command line, type and run this. If you are using an online coding editor, you should be fine. Okay, let's look at the examples. First, import the library. NumPy is often named as NP for short. The first one is a one-dimensional array. Looks like a list, but it's a NumPy array, more powerful and faster. The second one is 2D array. This is a matrix, like a table. There are rows and columns. The third one is 3D array. Think of this as a stack of matrices, like a cube of numbers. It's useful for image data and scientific simulations. Next, NP zeros. Imagine you want to start with an empty grid or prepare a clean slate before filling in data. That's where NP zeros comes in. It creates a NumPy array filled with all zeros. It's like saying, give me a blank page, please. The first example is a one-dimensional array with 5 zeros. The next one is 2D arrays. It gives you a 3 rows and 4 columns matrix filled with zeros. The last one is 3D arrays. It creates a 3D block with layers. Great for 3D models, video frames, or advanced data work. If you want to check the shapes, dimensions, and data type, you can use these methods. Next, if NP zeros is like a blank canvas, then NP ones is like a canvas already filled with 1, useful when you need a base value other than 0. It's great for initializing weights, masks, counters, or just creating dummy data. Next, NumPy full. So far we've filled arrays with zeros and ones. But what if you want to fill an array with any number? That's exactly what NP full is for. It's similar to NP zeros or ones, but you need to give the number you want to fill the array with. In this case, it's 9. Next, NP arrange. It's like a NumPy version of range method. Imagine you want to create a sequence of numbers like 0, 1, 2, and more. Python has range method, but NumPy gives you more control and flexibility with NP arrange. The basic syntax is this. Start is the beginning value, default is 0. Stop is the end value. Step is the difference between values, and default is 1. Let's check the examples. The first one starts at 0, ends before 5, step is 1. The second one starts at 3, stops before 10. The third one counts by 2. The last one set negative step. Great for countdowns or reversing. Next, NumPy linspace, which means generating linearly spaced values. Imagine you want to create exactly 5 numbers between 0 and 1, including both ends. That's something NumPy arrange cannot do easily because you have to guess the step size. But NumPy linspace can do it. The basic syntax is this. You need to give start, stop, and num how many values you want. Default is 50. Let's check it with the example. Let's say you want to generate 5 numbers, evenly spaced numbers from 0 to 1. The outputs show the numbers are evenly spaced, and it includes both 0 and 1. Next, NumPy. Have you ever seen a matrix where all the numbers on the main diagonal are 1 and the rest are 0? That's called an identity matrix, and it's super important in linear algebra and machine learning. This creates a 2D identity matrix, which is a square or rectangular matrix with 1s on the main diagonal and 0s everywhere else. It's like the matrix version of the number 1. Multiplying anything by it doesn't change the result. The basic syntax is this. N is the number of rows. M is the number of columns. M is optional, if not given, creates an n-square matrix. Key is the index of the diagonal. Default is 0, which means the main diagonal. Let's check the examples. The first one creates a simple 3 by 3 identity matrix. The second one is not squared. Still has ones on the diagonal, but it just stops early. The last one changes the k parameter. The diagonal is shifted one place up. Next, NumPy identity. It creates an n by n identity matrix with ones on the main diagonal and 0s everywhere else. This is essentially a shortcut for NumPy. This is always square. Only takes one argument. This is super clean and perfect when you don't need custom shapes. Next, NumPy random rand. Sometimes you want to create random values to test your code, simulate data, or build machine learning models. That's where this method shines. It generates an array of random numbers from a uniform distribution between 0 and 1. That means each number is equally likely. And all values are between 0 and 1. 0 is inclusive and 1 is exclusive. Let's check it with the examples. The first one generates a single random value. The second one is 1D array of 5 random values. The third one is 2D matrix of random values. If you want to get the same random numbers every time, you can use a seed. That is the last one. You can use any integer in the seed. The seed just tells NumPy, start your random number generator from this specific point so I always get the same random numbers. Then you can get the same numbers. But why does everyone use 42? It's a reference from a famous sci-fi book. In the story, a supercomputer is asked to find the answer to the ultimate question of life, the universe, and everything. After a very long time, it replies, the answer is 42. So ever since then, programmers and data scientists around the world started using 42 as a fun default seed value when working with random numbers. It's like an inside joke in the tech community. This is often used when simulating data or noise, testing models with random inputs, initializing weights in machine learning, creating random patterns, games, or visuals. Next, we've already seen NumPy random rand, which gives numbers evenly spread between 0 and 1. Now imagine you want random numbers that cluster around a mean, like real-world data such as height, IQ, exam scores, and so on. That's where NumPy random random comes in. It generates random numbers from the standard normal distribution. As shown in this graph, mean is 0, standard deviation is 1. So most values will be near 0 and fewer will be far from it, mostly -3 to +3. Let's check the examples. The first one is a single random value. The second is 1D array of 5 random values. The third one is 2D matrix of random values. This is useful for simulations and modeling real-life randomness. This is a quick summary of random randomn. Next, randint. Up until now, we've worked with random floats, but what if you want whole numbers like rolling dice, picking a random ID, creating test labels? That's exactly what this is for. It generates random integers between a start and stop value. So if you say randint17, it gives you a random number from 1 to 6, just like a dice roll. Let's check the examples. The first one is a single random integer. Generates random integer between 1 and 9. The second is a 1D array of 5 random integers between 0 and 4. The last one is a 2x3 matrix with values from 10 to 99. Next, NumPy empty. Imagine you're creating a big array just to fill it later. You don't care what's in it right now. That's where NumPy empty comes in. It gives you an array with the right shape, but the values are random junk. Not 0 small number. It creates a new array without initializing its values. So you get the right shape, but the contents are random leftover data in memory. It's very fast, no time wasted setting zeros or ones. Okay, let's check the examples. The first one is a 1D empty array. It's like a random garbage. The second is a 2D empty matrix. Right shape, but weird numbers. The third one is empty with int type. The default data type is float, but you can change it like this. You can use this when performance matters and you'll overwrite values anyway. Also, pre-allocating space before filling in a loop. If you want clean values like 0 or 1, use NumPy zeros or NumPy ones instead. Next, NumPy from function. You want to generate a pattern, a grid, or apply a math function to fill an array. Then NumPy from function comes. It gives you full control by letting you define a rule to fill each value based on its position. It creates an array by calling a function on each index like row, column, depth, and so on. This is the basic syntax. A function takes index coordinates like I and j. The shape is the array you want. The default data type is float. Okay, let's check the examples. The first one creates a simple grid. It creates a 3x3 array where each element is calculated by row index value plus column index value. Anyway, what is lambda in Python? A lambda is a short anonymous function, kind of like a mini function. So this is the same as this. The arguments come left and the expression comes right. The benefit of lambda is that you can define the function in line inside another function. The second one is the multiplication table. Classic use case for math patterns. The last one is a 3D example. So it works with any number of dimensions. So you can use NumPy from function when generating grids, maps, or mathematical tables, creating test patterns for image processing, filling arrays based on index logic, and when you need full control over what goes where. Three, array basics. 1. Array info and structure. These tools help you inspect and understand your NumPy arrays. Think of them as the way to ask questions about your array. What does it look like? How big is it? What kind of data is inside? Let's go through the 6 essential properties. First, ndim. Let's say you have a 2x3 matrix, and dim outputs 2. Ndim stands for number of dimensions. So a 1D array is like a list, ndim is 1. A 2D array is like a table shows ndim 2. A 3D array is like a cube of data shows ndim 3. It's like asking how many axes does this array have? Next, shape. It returns rows and columns. So it outputs 2 and 3. This means the array has 2 rows and 3 columns. Shape returns a tuple of dimensions. It's useful for reshaping and validating array sizes. Next size. Total number of elements. It outputs 6. Tells you how many total elements are in the array. Great for quickly checking how much data you're dealing with. It's equivalent to rows by columns for 2D arrays. Next dtype, data type of each element. It outputs in 32 or in 64 depending on your system. It tells you what type of data the array holds. Next, item size. Memory size of one element. It outputs 4 bytes for each and 32 element. It shows how many bytes each element takes in memory. So it's useful for understanding memory usage and optimizing. Finally, n bytes, total memory usage. It outputs 24 because there are 6 elements and 4 bytes each. It's a total memory used by the array in bytes. It helps when working with large data sets and tracking memory. 2. Type conversion. Sometimes you'll want to change the type of values in your NumPy array. Maybe you started with integers but need decimal precision. You loaded string data and want to convert it to numbers. Or you're preparing data for machine learning where type matters. That's where NumPy as type comes in. IsType creates a new array with the same shape but a different data type. It does not change the original array, it returns a new one. Let's check the examples. The first example converts integers to floats. The second one converts floats to integers, just removes decimals. The third one converts numbers to strings. The last one converts numbers to Boolean. 0 is false, others are true. Three, reshaping and flattening arrays. Arrays are like building blocks. Sometimes you want to stack them differently. Maybe turn a long row into a table or flatten a matrix into a single line. That's where reshaping and flattening come in. Think of it like folding and unfolding a map. It's useful when you do pre-processing data for machine learning, changing image dimensions, performing matrix multiplication, managing large data sets. Okay, let's check step by step. First, reshape. Use this when you want to transform the structure without changing the data. Let's say you have a 1D array with 6 values. The first example changes it to 2D array, same values and new structure. The second one is 1D to 3D. So now you have 1 2x3 matrix inside a 3D array. Next, if you don't know the exact shape you want, let NumPy calculate it for you. Let's use -1 to let NumPy autofill. In this example, column is 2, and NumPy automatically figures out the number of rows. This is very handy for batch reshaping in machine learning or pre-processing. Next, flatten. It turns any array into 1D. Sometimes you just want to take a matrix or a multidimensional array and lay it all out in a straight line, like unrolling a carpet. That's exactly what flatten does. In this example, the original array was a 2D array, but the flatten method returns a flat 1D array with all values from left to right, row by row. You can use this when you prepare input for machine learning models, which often want flat inputs. Next, revel. It also flattens a multidimensional array into 1D. But instead of returning a full copy, it returns a view of the original array. That means it's faster and uses less memory. So the output in the example shows the same flattened result as flatten, but behind the scenes it's just a view, not a copy. So you can use it when you're working with large arrays and want better performance. And when you don't need a separate copy, also memory efficiency matters. 4. Transposing. Have you ever wanted to turn rows into columns and columns into rows? That's what transposing does. If you're working with tables, images, or matrices, it's a super useful trick. Let's break it down together. You can transpose a NumPy array using these two shown in the table. They both do the same thing for 2D arrays. For example, in this case, the original array is 3 by 2. By using transpose, the rows and columns are flipped. You can use this for matrix multiplication, like machine learning, stats, linear algebra. Others are rearranging data sets and switching x and y axes in plotting. 5. Copy. Imagine you're working on an array and you want to tweak it, but you also want to keep the original version safe and untouched. That's when you reach for this method. This is like saying, give me an identical clone, but keep it separate. Let's check the example. A is a NumPy array storing 3 values. B is A's copy, which has the same data as A but is stored in a different place in memory. Then change the first element of B and print. The original A array stays the same, only B is changed. So you can use this when you need to try something without affecting the original. 4. Indexing and slicing. 1. Basic indexing. These are the basic indexing. Imagine a NumPy array is like a row of boxes or a table, and you want to reach in and grab a specific item. That's exactly what indexing allows you to do. First, 1D array indexing. A 1D array is like a simple list. To access the first element, give index 0. Same as a list, the index starts from 0. The fifth element is index 4 or minus 1. Negative indices count from the end. Next, 2D array indexing. Now let's level up to a 2D array, like a table. Let's say you have a 2 by 3 matrix. The first indexing means row 0, column 0. The second one is to access 6. You can access element using 2 steps, but less common. And also you can use negative indexing to access the last row and last column. Two, slicing. Slicing is like saying, hey NumPy, give me a portion of this array, just the part I need. So you can slice rows, columns, whole ranges, even skip elements with steps. Let's go through each slicing technique one by one. First, slice 1D array. In this case, it starts at index 1, then stops before index 4. 1 is inclusive, 4 is exclusive. So you get elements at index 1, 2, and 3. Next, slice with a step. The example means start at index 0. Go up to, but not include, index 5. Take every second element. Next, slice specific row in 2D. This example means you're looking at row 1 and grabbing columns 0 and 1. Next, slice specific column in 2D. This grabs all rows from index 0 and 1 just for column 2. Next, full array, no slicing. This just returns the whole array, often used as a placeholder when you'll modify a slice later. Next, all rows from a specific row. The example means skip the first row and grab the rest. Next, all columns from a specific column. The example means keep all rows but only columns 1 and 2. 3. Boolean indexing. Boolean indexing lets you filter, select, or change array elements based on a condition. It's like saying, hey NumPy, show me only the values that match this rule. Okay, let's walk through each method one by one. First, filter all elements greater than 0. Let's say you have a NumPy array including positive and negative numbers, and filter values. This gives you only the elements that are greater than 0. Next, filter all even numbers. This example means give me only the values that are divisible by 2. Next, condition a new value. This example replaces all negative numbers in the array with 0. Four, fancy indexing. Fancy indexing means indexing with style. Instead of using just one index or a slice, you use lists or arrays of indices or Boolean arrays to pick exactly what you want. It's perfect for grabbing multiple specific values at once. First, select multiple rows or elements by index. Let's start with a simple 1D array. Let's say you have a simple 1D array and want to get the index number 0, 2, 4. This example means give me the elements at positions 0, 2, and 4. So you're passing a list of indices to access multiple elements at once. Next, select multiple specific elements from a 2D array using pairs of positions. Let's say you have a 2D array and want to access two numbers. 0, 1 refers to the element at row 0, column 1, which is 2. 2, 2 refers to the element at row 2, column 2, which is 9. Each position is picked by pairing the same index elements from the two lists. The first part is row indices and the second part is column indices. Next, select using a Boolean array, also called a mask. This example means only elements where the mask is true are selected. This is very similar to Boolean indexing, but it lets you manually control which positions you want, not based on a condition, but based on a custom true or false pattern. Fancy indexing can be used when applying masks from machine learning, image processing, or stats. 5. Where and non-zero. Both of these functions help you find the positions or indices of certain elements in a NumPy array based on a condition. Let's explore them one by one. First, where? It returns the indices where the condition is true. Let's say you have a simple 1D array and want to get the numbers greater than 0. Write the condition in the where method. Then you get this output. It means index 2 and 3 are where the condition is true. The values are 3 and 5. You can use the result to grab the actual values by giving indices like this. Also, you can use it like if-else statement. NumPy where can also work like a vectorized ternary operator. This example says, for each value in grades, if it's 50 or higher, return pass. Otherwise, return fail. This is useful because no need for loops or if statements. Super fast, works with large arrays. Makes your code clean and readable. Next, NP non-zero. It returns the indices of all non-zero values, great for sparse data or filtering out blanks. The output means that values at index 1, 3, and 4 are not 0. You can get the actual values by passing indices. Five, array operations. 1. Arithmetic operations. In NumPy, you can do math on entire arrays without using loops. This is called vectorized operations or element-wise operations, and it's super fast and beginner-friendly. Let's go through each operation with examples and explanations. First of all, let's say you have two NumPy arrays. A holds 10, 20, 30. B stores 1, 2, 3. We'll apply operations to these arrays element by element. For example, addition. Each element in A is added to the corresponding element in B. 10 plus 1 equals 11. 20 plus 2 equals 22. 30 plus 3 equals 33. Subtraction, multiplication, and division behave similarly. These are simple element-by-element calculations. Next, exponentiation. In this case, each element in A is squared. 10 to the power of 2 equals 100. 20 to the power of 2 equals 400. 30 to the power of 2 equals 900. You can also do that with B. 10 to the power of 1 equals 10. 20 to the power of 2 equals 400. 30 to the power of 3 equals 27,000. Next, modulus. Modulus means remainder after division. For example, 10 divided by 1 equals 10, and the remainder is 0. The rest is the same. 2. Aggregate functions. Aggregate functions help you quickly summarize a NumPy array. You can get totals, averages, maximums, or even find where the biggest or smallest value is. Let's go through each function step by step. First of all, let's say you have a simple NumPy array with 5 numbers, 10, 20, 30, 40, and 50. First sum, it's a total of all elements, outputs 150. Next mean, it's an average. In this case, the total sum 150 divided by the number of elements 5 equals 30. Next median, it's a middle value. If the array had an even number of elements, NumPy would average the 2 middle ones. Next, standard deviation. This measures how spread out the values are from the mean. The higher the standard deviation, the more the values differ from the average. The output is 14.14. It means most numbers are about plus or minus 14.14 units from the mean of 30. Next, variance. It's another way to measure spread. The difference between variance and standard deviation is that standard deviation is just the square root of the variance. So in this case, variance is 200. The square root of 200 is 14.14. Next, minimum and maximum. They return the smallest or largest value in the array respectively. The last two are the arguments of the minimum and maximum, which return the index number. For example, the argument of the minimum is 10 and its index number is 0. Three, comparison operations. These operations let you compare two arrays or an array with a value and get back a new array of true or false values based on the condition. This is the foundation for filtering, masking, and Boolean indexing in NumPy. Let's check one of them. Let's say you have two arrays, A and B, and compare using equal. Each element in A is compared with the corresponding one in B. 10 and 10 is true, 20 and 25 is false, 30 and 25 is false. The rest of them behave similarly. Compare arrays element by element and return true or false. Four, logical operations. These operations allow you to combine multiple conditions, use logical and or not, and filter arrays with more control. Let's break it down with examples. First of all, let's say you have a simple NumPy array with 5 numbers, 1, 4, 8, 12, and 3. First, logical AND. It returns true only when both conditions are true. In this case, 3 to 9 can meet the conditions. Next, logical OR. It returns true if either condition is true. Next, logical NOT. It flips true to false and vice versa. For example, if you already have a Boolean array, it flips true to false like this. Next, the last two are the shortcuts of AND and OR. For example, you can write something like this. These are simpler and easier to read. 6. Broadcasting. Broadcasting allows NumPy to perform operations between arrays of different shapes without writing loops. It's like saying, "Hey NumPy, stretch this small array to match the shape of the big one, then do the math." Let's break it down with examples. First of all, let's say you have a simple NumPy array with 3 numbers, 1, 2, and 3. The first operation is an array with a scalar. The example means adds 5 to every element in A array. No need for a loop. But why it works? Because 5 is a scalar, just one number. So NumPy can broadcast 5 across the whole array. The second operation is a matching shape. The example means multiplies each element of A by the corresponding value. So this is an element by element multiplication. If shapes match both 1D with 3 elements, it's just basic vectorized multiplication. The last one is about handling different shapes. For example, let's say you have a 3 by 1 array called A and a 1 by 3 array called B, different shapes, and want to add these two. NumPy automatically reshapes and aligns arrays. Then you can get a 3 by 3 matrix. When performing operations on two arrays with different shapes, NumPy follows these rules. 1. Compare shapes starting from the last dimension, right to left. 2. Dimensions must be either the same size or one of them is 1, which can be stretched. If they're not compatible, NumPy raises an error. 7. Linear algebra. These operations go beyond simple element-wise math. They treat arrays like real mathematical matrices. Let's go through each method with easy examples. First of all, let's say you have two 2D arrays. A and B is shown at the left bottom. The first method is a matrix multiplication. A.B and NumPy.a, B show the same result. It performs matrix multiplication, not element-wise, so the output is 19, 22, 43, and 50. Why did we get this result? Let's go through the calculation step by step. Now we're multiplying these two 2 by 2 matrices. The result will also be a 2 by 2 matrix. To calculate the value, let's assign positions like this. Then calculate each position like multiply the row of A by the column of B and sum the products step by step. First, the positions of 0 and 0. Multiply the first row of A by the first column of B and sum the products. The result is 19. Do the same thing to the others. Finally, we get the matrix multiplication result. The second method is also matrix multiplication. This is exactly the same as the first method, but cleaner and preferred in modern Python. The third one is also matrix multiplication, same as previous ones for 2D arrays, but more powerful when dealing with 3D arrays and batch matrix multiplication. Next, transpose. It flips the matrix over its diagonal, rows become columns. The last two are inverse and determinant. What are inverse and determinant? When you're working with 2D arrays, you might want to undo a transformation, solve a system of equations, check if a matrix can be inverted. That's where the determinant and inverse come in. What is the inverse? The inverse of a matrix is like dividing for matrices. I is the identity matrix. It's like 1 inch in matrix land. On the other hand, the determinant is a single number that describes something important about a square matrix. You can think of it as, how much does this matrix stretch or squish space? If the determinant is not 0, the matrix is invertible. It has an inverse. If it's 0, the matrix is singular. You can't undo it. As you can see, the determinant is in the inverse. So when you calculate the inverse, you need to find the determinant first. Summary. We walked through these topics. Let's quickly review all the learnings. 1. What is NumPy? NumPy is a core Python library for numerical computing. It's mainly used for working with arrays, performing mathematical operations, and handling linear algebra efficiently. 2. Creating arrays. This section shows different ways to create arrays. Manually with NumPy array filled with zeros and ones, sequences with NumPy arrange and linspace, identity matrices, random values, and empty arrays. 3. Array basics. These methods let you inspect and manipulate array properties like shape, size, and data type. You can also reshape arrays, flatten them, or transpose them for further operations. 4. Indexing and slicing. This section covers how to access parts of arrays such as indexing, slicing, and conditional filtering using NumPy where and NumPy non-zero. 5. Array operations. Arithmetic, do math directly on arrays such as add, subtract, and multiply. Aggregate, compute sum, mean, median, etc. Comparison, compare elements to get Boolean results. Logic, combine conditions using logical and or not. 6. Broadcasting. This allows you to apply operations between arrays of different shapes. For example, add a scalar to an entire array or match a 1D array to a 2D array's rows or columns. 7. Linear algebra. Useful for math-heavy tasks such as matrix multiplication, transposing, inverting matrices, calculating determinants. These are the foundational tools you'll use again and again in data science, machine learning, and beyond. If you're just getting started with Python, learning NumPy is a huge step forward. Don't worry if it feels like a lot at once, that's totally normal. The more you experiment and use these functions in your own code, the more natural it will all become. Try building something simple, analyze some data, or even challenge yourself to rewrite your old Python code using NumPy arrays. Okay, thanks for watching today's lesson on coding Fab. I hope you found these tips useful and feel more confident. Remember, practice makes perfect, so try using these tips in your project. If you enjoyed this video, don't forget to give it a thumbs up, share it with your friends, and subscribe for more Fab coding lessons. Until next time, keep practicing and stay Fab.